Today we will go through dynamic head, unifying object detection head with attention. We will implement it from scratch, and we will also compare it with the official implementation. The idea of implementing from scratch is really to understand what's going on, and actually this dynamic head module is also in glib paper, which I was going to implement. This is a multimodal image text model which can be used for open object detection, and they're also using dynamic head module, so it makes sense to first implement this. Okay, going back to dynamic head. So their main idea is they are coherently combining multiple self-attention mechanisms between features, scales, and spatial locations. And they demonstrated with the different object detectors that dynamic head achieved quite good performance with different backbones and with single stage object detector like SSD, YOLOS, FCOS, and also two-stage object detectors like fast RCN and those things. Right, let's just directly go to what's going on here. So this is the architecture of this model, and for object detector what we have is first the feature pyramids. So if you're not aware, we have for object detectors we have these multiple pyramids of features. So as the images go through these different layers, the spatial dimension is reduced, so that's why these features are smaller in spatial size, but the number of channels or features increase. And the idea is for the bigger features we can detect smaller objects, and for smaller features we can detect bigger objects. So that's the main idea of having this multiple feature pyramid. As you go through this paper, it's I think quite good. Okay, so this is, we have the feature pyramid here. We have levels, we have spatial size and channels. So essentially what they did was they combined these three attention mechanisms sequentially rather than doing it at once. Because doing it all at once in all these different dimensions is very computation expensive. It's of quadratic nature. Self-attention, and we have L, S, and C. If just you do attention on top of that, it is quadratic. It's very expensive, so they do it one by one and have them sequentially, so the cost goes linearly. For scale attention, we have first there's a message passing kind of between different scales, which is given by just lambda L. We also have feature passing or message passing or between different spatial positions, which is given by lambda S, and we have between different channels for different kind of task. So essentially in object detectors what we have is we have a backbone, and then we have different branches. One can do object classification, the other branch can do center regression or bounding regression, depends on what kind of object detector you have. So for classical object detectors like mask RCN, we have bounding box regression, but for something like FCOS or CenterNet, we have this kind of center of the object regression. But you have some kind of regression there. And the idea is these behaves or these branches learn different things. So that's why we have these different branches after the backbone. But in this paper, what they say that they can combine all of them into one, known as dynamic head, which can capture details from all these different dimensions. Let's just directly go through what this dynamic head is. And they have given some more motivation why they do that. But let's just go directly to the implementation, what's happening. So this is dynamic head. Given the feature tensor of L, S, and C, L is the number of levels. So these blue things, these are the three levels in this diagram. S is the spatial size, which is height and width, and C is the number of channels. So if you think about in torch, it's normally L, S is basically divided into two, but you can just flatten it up into S, and then we have C also. So yeah, they're saying here that we can have this self-attention across all these dimensions, and lambda can be self-attention, but this will be very computationally expensive, right? So what they do instead is they convert this self-attention into 3 sequential attentions, focusing only on one dimension on perspective. So yeah, this is kind of the nested or composite function. We start from the middlemost. So we have attention across the level dimensions. So across levels, we have attention, and then it's multiplied by the input feature. Then we have the attention across spatial dimension, and then it's multiplied by the input feature, and then we have the output of that is the attention level across channel dimension, and then it's multiplied by the features. So a bit more detail I think now. So the first is scale level attention, and if we go through this, so what they do is basically take the average across scale and channel dimension. So this can be implemented as a mean operator or global average pooling, kind of the same thing in Torch. So yeah, so they reduce 2 dimensions here. So they take the mean across scale and channel dimension, and then if we go to the original tensor, if you take the mean of that, then we're left with only L dimension. And of course we are trying to take the attention across levels, so we have reduced the other 2 dimensions. Then we have this f function, which is it's a linear approximated by one convolution, and then we have this sigma nonlinearity, which is hard sigmoid function given by this. So this adds a nonlinearity to this attention thing. And then we have this attention maps, and then these are multiplied with f. I will go over through the code part of how this is I've implemented this. After the level attention, we have spatial attention. And what this will do is essentially capture the relationships across the spatial domain, so across height and width of the image domain. And this is implemented like this. So this looks a bit complicated, but essentially what it is this is deformable convolutions, and you can see, consider high dimension S. Because S is high dimensional, we decompose this module into 2 steps. First, making the attention learning sparse. Yeah, so they don't want to learn attention across each spatial point because it's high dimensional, so they want to make it sparse, and deformable convolution is a nice way of doing it. If you don't know what deformable convolutions are, this is the paper for deformable convolutions. So in regular convolution we have this grid, and this each convolution kernel can only look at this grid, which is a regular grid. And there's another type of attention, convolution. It's called dilated convolution, in which we can have a hole in between these grids. So without increasing the number of parameters in convolution, it can have a bigger receptive field. But the deformable convolution now take it really to the next step, and what they basically say is that we can have these offsets from the center point not fixed, not in a regular grid, but they can be learned itself. So they can learn arbitrary transformations, and yeah, basically for non-rigid objects they can really look at the places where a regular convolution cannot look at. For example, D, they can see like the same 3x3 kernel can look at different places where the regular convolution receptive field cannot reach for the same layer. And I think there's a nice image here also. If you see the standard convolution, it can only make a regular grid, but for deformable convolution it can really look at these it can deform and look at the different parts of a non-rigid object, which doesn't conform to a square shape. Okay, coming back to this paper. So what we do is apply deformable convolution first across the spatial domain. And so this is for deformable convolutions. We have W is the weight. We have P are the offsets. You can see PKs are the offsets. Delta M is the masking factor, so it's a sigmoid masking factor, so it can turn on and off any of these offset points. Deformable convolution across the spatial domain, and then we also take the mean of the levels. And then finally we have the third kind of attention. After we have scale level attention, we have spatial aware attention, and then finally we have task aware attention. And this will be across different channels. And essentially what it does is dynamically switches on and off the channel in favor of different tasks. And the main idea is that the final task can be very different. For example, one of the tasks can be for the network object detector network is to have classification, like classify into different classes. And the task, for example, for something like CenterNet is the center point regressor. For an ordinary object detector, mostly it's like bounding box regressor, but it can also be key point regressor, right? So there are different kind of tasks, and normally what object detector does is to have different branches of all of these tasks. But the main idea is that if we have this task aware attention, then you don't need to have different branches, and you can just have this single dynamic head which does this attention across all three levels, and just in the final stage you can have these different tasks without having separate branches for all of them. And what this equation does essentially, so if you look at it, it looks very similar to ReLU, and actually it is kind of ReLU but across channel dimension. We have these learnable parameters. So FC is the feature slice at the C channel, and so these features are learned, and their size is the size of the channel dimension. So they want to turn on and off each channel depending on the task. So what they say here is it's implemented similar to equation 3, which first conduct a global average pooling on L and S dimension. So in channel 3 we are doing pooling across scale and channel dimension, but we don't want to do across the channel dimension now. We want to do scale and level dimension. And then they use the fully connected layer and normalization layer, and finally by a sigmoid function, and then take it from -1 to 1. So in the end we have this equation. It's kind of very similar to ReLU, and I can show also why this is similar to ReLU here. So because the initial conditions of these parameters are 1, 0, 0, 0. So if the lambda 1 is 1 and this is 0, rest is 0. So this becomes actually max max of f of c and comma 0. So which, and fc is the input, so it exactly becomes ReLU, but this is like learnable ReLU. So finally this is the architecture of how everything is connected. We first have attention across different levels. We have then attention across different spatial size, and then we finally have attention across different channels. Okay, now let's go back to the code and show how I implemented this, and we can refer back to this diagram and see if it makes sense or not. I will also go to the official implementation. So this is the official implementation of this dynamic head block, which you can also use. I find it a little bit hard to read and understand, especially comparing to this workflow. Okay, let's go over through the code of dynamic head. So this is the code of dynamic head. It's also available on my GitHub. We'll also share in the description. What it does is essentially passes the input feature channel dictionary through 4 modules, and we can go through one by one each of them. So first one is multi-level fusion. So it has two purposes. First, it maps the channels to the number of output channels for each feature level, and secondly, it also upsamples or downsample the consecutive features to the median level feature. And what it is coming from is through this part of the paper. So given a concatenation of features from L different levels, we can resize the consecutive level features to the scale of median level by upsampling or downsampling them. So essentially what we do is we'll go over through each of these feature level, and if the neighboring feature level exists, we either upsample them or downsample them to the median level. For example, if we are currently at the middle level, we will downsample the previous feature channel to this dimension, and we will upsample the next feature level to this feature level dimensions. In this way we can concatenate them, so then the spatial sizes of these consecutive feature level become the same, and then we can apply the attentions which are needed for the next step. If we go over to the code and see what it is doing, then we go directly to the forward pass. So it is first aligning all the feature channels to the same number of features, which is the output feature. If we go here, what this one is doing, self-dep channel maps, is building a dictionary which maps from input channel to the number of output channel, which are the input to this module. So that's the first thing it does. Second thing it does is go through each level of feature channel and kind of gets what I just described in the paper. So it goes through each level, append the current feature to this list. Then it looks if it is not at the borders, at the start or the end. If it is not, then actually it gets the previous convolution and downsample it. So the previous convolution has stride of 2. So because the previous feature channel normally has a bigger spatial size, so we downsample it to the current feature level. And if we have the next feature level, then we kind of upsample it to the current feature level, and we append all of them into the list. So first the current feature level goes to the list, then the previous goes to the list if it exists, and then the next goes to this list if it exists, and then it is returned as a dictionary also. So output dictionary has the same keys as the input dictionary, but the output features for each of that is a list of feature channels. The next module is scale aware attention. So what we got after multi-level fusion is we mapped the number of channels to our output channels for each feature level, and we also have now the consecutive feature list for each dictionary item. For scale aware attention, what we want to do is implement this part, right? So the input goes to average pooling, goes to one by one convolution, a ReLU, a hard sigmoid, and then the output of this is multiplied by the input feature levels. And this is exactly what the scale level attention will do. So it goes through each feature dictionary, gets the current feature level because it will be then later on multiplied with the attention across the levels, and it also passes this feature through this attention, which is exactly what's described in the paper. It's average pooling 2D, which kind of reduces the output size, spatial size to 1. It passes through one by one convolution, which output channel also 1, so it also reduces the spatial size. It passes through ReLU, and then finally it passes through the hard sigmoid, and then multiply the input features, this input feature stack features to this attention. Right. So this is, and you can also go through this equation, you can satisfy that this is actually doing this. It is taking the mean across spatial and also reducing the number of channels to 1, passing it through 1 across 1 convolution. Actually ReLU they have not mentioned it here, but in the diagram they showed that they pass it also through ReLU before passing to hard sigmoid. So that's what we are doing, and also in official implementation they pass it through ReLU first. So now we have the level attention. Next we want to do is spatial attention. And spatial attention is essentially we perform deformable convolution on each feature level, and then we take the mean across the level dimensions. Right? And this diagram is actually also showing this. So first we get the current feature level, we perform a 3x3 convolution, we get the offsets and sigmoid for deformable convolution. So this sigmoid output is this mask, and these offsets are what are also required by the deformable convolutions. So those are learned offsets for this deformable convolution, and then finally we take, this is the convolution operator, and then we take the mean across the levels. And if we look at the code, this is a spatial level attention. We again go through the input dictionary, we get the current features, which is now the list, if you remember from the previous one. Is the current feature level and also the neighboring feature levels. So the current feature level is always the first one, right? So if you remember from the previous one, so multi-level fusion, our current feature level goes first, so it is in the 0th dimension, and then the previous and the next one goes. So we get the first feature level, we calculate the offsets and mask for deformable convolution from the current feature level. And I can also explain a little bit why it is 18, and I've written actually also it here. So for 3x3 convolution which we are using, the number of offset will be 3x3 is 9 multiplied by 2, because for each 9 positions we have 2 offsets across x and y for 2D convolutions, right? So we will have 18 offsets, and then we will have 9 masks, and each of these offset can be turned on and off, and that's why we have these masks. So this will become the convolution arguments for deformable convolutions, and then we just capture all of them in a list and stack it across the 0th dimension, and then take the mean, right? So this will become mean across the level dimension, and then the output is the same as the dictionary, but now the level dimensions is also normalized or taken mean of. And then finally we have task level attention. So we have multi-level fusion, scale level we have done spatial aware attention, now finally we have task aware attention. And what it does is very similar to the first step. It takes the average pooling, and then it learns these parameters alpha 1, beta 1, alpha 2 and beta 2, and also given these initial conditions, and then multiply the input with these parameters. This is exactly what's happening here. We get the feature which is now of shape BCHW. We take the average pooling, so we normalize or cancel out H and W to only 1 because it is passing through global average pooling. So when it passes through this, H and W will become N1, and we will have B, C, 1 and 1. And then we reshape into B and C. Then we pass it through this fully connected or linear layer, which is just linear ReLU, linear sigmoid, and the output number of channels of this is 4 multiplied by output number of channels. So we have 4 parameters, and dimension of each is b cross c. Right, so parameters are initially b4c, and then we separate it out or chunk it out using just very simple indexing. Then according to paper, we also have to normalize it between -1 and 1, and that's what we are doing here. And you can also satisfy it because the lambda is 1 and we multiply by 2. So the range of this alpha 1 will be from -1 to 1, and same for all the other parameters. We also add an initial condition of given by the paper, which is 1 0 0 0. So like I mentioned before, it will become exactly like ReLU initially, but then when these parameters are learned, it can be anything else depending on the task. And finally we apply out the equation 5 of the paper, right? So which is this. So we have alpha 1 which is calculated from feature multiplied by this input feature, and then plus beta 1 and alpha 2 calculated from this feature multiplied by fc, which is a slice of the feature across the channel dimension, plus beta 2. And this is exactly what we're doing, and then taking the max and returning output, right? So we go through the forward pass of dynamic head. We pass it first to the fusion module, which converts all the level features to the same number of channels, and also gathers the neighboring feature levels and convert them to the same size so we can perform the next task. Then we perform scale level attention, which essentially calculates the attention map or attention weights across the scales. Then we do spatial level attention, where we use this deformable convolution to have sparse attention, because spatial attention is very expensive if we do fully. And then finally we have task level attention, which is just across the channels, and it can dynamically turn on and off the channels. So this is the whole motivation, and the idea is we can stack all these dynamic heads one after the other. So we can stack them all together, and instead of having separate branches for each of these heads, we can just stack them, and then finally we can have this classifier or bounding box regressor instead of having separate branches. Okay, let's just test this implementation. So I will also share the GitHub repo of it. So we have this test.py. If you look at it, the input is this dictionary of features with the keys and values. So this is just dummy data right now, but you can also use TIM library and use pretend model, and you can get the feature pyramid from it and then pass it through this dynamic head. It initiates the dynamic head with the input and output channels and pass the outputs, and then we can print out the shapes of the input and output. So for example, if I do test.py, right, so you see that the input is 2 56 64 64 32 32 16 16. So it's typical scale pyramid that we get out of bounding box of the backbones. So we have increasing number of channels but decreasing number of spatial size, and the output we got the same number of output channels. It's what we described during the multi-level fusion of features, but then the spatial size is the same as the input, right? Okay, finally let's go to the official implementation of dynamic head. So this is from Microsoft, and this is what's happening in this dynamic head. So this is much more compact, but I think a little bit convoluted to follow along. But if you really look at it, you will understand that these are the same thing which is happening. So what I described before, we go through each feature level in the feature dictionary. We calculate the offset and masks for deformable convolutions. We resize these features to the median level, then we append it. Then we have this attention convolution, which in our case was level aware attention, where we take the global pooling, conv, and relu. Then we append it to the list, stack these features, pass it to a hard sigmoid, multiply both of them, and take the mean across the zero dimension. So this part now is part of the spatial level attention, and actually deformable convolutions they have already did before, and now this mean across the level dimensions is taken here, and then it passes through the ReLU, which is the same as task level attention. And if you go through their implementation of dynamic ReLU, you can go through it, but it's very similar to what we did, but it's just more general if you want to use 2 parameters or 4 parameters. Yeah, so I think that's it for it, and in next video I will implement it for clip paper, and if I have some time I will also implement it as a downstream for different object detectors.